Now, there are some particularly useful ways that you can employ factoring to deal with expressions that contain squared values, that is, values with an exponential of 2.
Suppose we need to subtract 4 from x squared. Well, 4 is the same thing as 2 squared, so we could rewrite this equation like this. Now, to subtract one square from another, you can use a technique called the difference of squares and refactor the expression like this, removing the exponentials. A perfect square is the product of a number multiplied by itself. So for example, 4 times 4 is 16, so 16 is a perfect square. Look at this expression, which includes a variable x and a coefficient and constant of which 3 is the common factor. We could refactor this expression like this, x plus 3 times x plus 3. But that's a number multiplied by itself. In other words, it's a perfect square. So we could rewrite it like this, x plus 3 all squared. Now there's a general formula for refactoring perfect squares in this format, and it's worth memorizing this. The formula is a plus b squared is always equal to a squared plus b squared plus 2ab. And you're going to find this really useful when you come to solve quadratic equations, which we'll cover later. In the meantime, let's just run through an example to prove to ourselves that it works. And in this case, for a, we'll use the value 2 instead of x, and we'll leave b with the value 3 like we had before. 2 squared is 4, 3 squared is 9, and 2ab is 2 times 2 times 3. Well, we can easily work out that our 2 plus 3 all squared is 5 squared, and 2 times 2 times 3 is 12. Now, do you remember our original equation? X squared plus 6x plus 9 was refactored as x plus 3 all squared. So the a component was x and the b component was 3. Well, with an x value of 2, x squared is 4 and 6x is 12. So you can see that the formula holds true. For a value of x, we've got exactly what we had with our original formula. Now, of course, when we've got the known values for both a and b, we can actually finish off both sides of the equation and see that the two expressions are indeed equal. In this case, our perfect square turns out to be 25.